Hi, in this video we will be talking about improper integrals. So exactly what are they, how do we identify them, and how do we evaluate them differently than the other integrals you've seen so far in class. So there's two types of them. We're going to discuss them right now. So type 1 is that one or both of the integral bounds are plus or minus infinity. So for example, the integral from 1 to infinity of x e to the negative x. So what makes it improper is the infinity at the top. The second type of improper integrals is that the function in the integral is discontinuous on the interval being integrated. So that's sometimes a little bit more difficult to understand, but the example that I have there is the integral from minus 2 to 3 of 1 over x dx. So the reason why this would be improper is because, for example, 1 over x doesn't exist at x equals 0. And notice that x equals 0 is in the interval from minus 2 to 3. So because 1 over x is discontinuous at one or more points in that interval, this makes it improper, and therefore we have to be careful when we evaluate it. We're going to do some examples to show you how exactly you would do that. Before we do an example, we're just going to talk about some terminology that's used with improper integrals, and you're going to see this very often in these questions. So if the integral equals a real number, we say that the integral is convergent, and otherwise we say it is divergent. So in the second case, this could be cases where the limit or the integral is equal to plus or minus infinity, or simply doesn't exist. And we're going to do cases to see what this looks like. Okay, so in this example that I have up here, we're doing integral from 9 to infinity, x e to the 3 minus x. Okay, so this is an improper integral of type 1 because of the infinity. So what we do first is we want to tackle down how to get rid of that infinity. We cannot take infinity as one of the bounds. So what we do is we write it as limit t approaches infinity from 9 up to t. So you're going to replace that infinity in the bound by t, and then everything else in the integral stays the same. Now what we're going to do is we're going to evaluate this integral first, and then we're going to sub in the 9 and the t, and then we're going to do the limit. So almost look at it as we're working right to left. Okay, all right, so in this integral we have x, and then we have e to the 3 minus x. So basically in this case we would use by parts. Okay, so I know that I have to use by parts because the x and the e to the 3 minus x, their derivatives are not similar and they don't have anything to do with each other. So this suggests that I use by parts. Okay, so I'm going to let u equal to x. And that means my dv is going to be e to the 3 minus x dx. And if you want to just review how to tell which one I choose as your u, which one is, I choose as a dv, just review my video on by parts. Okay, so du, then the derivative of x is just 1 times dx. And v, when I take the integral of the e to the 3 minus x, I'm just taking the antiderivative. So this gives me, I just copy and paste the original function and divide by the derivative of the exponent, which the derivative of the exponent is minus 1. So now I'm just going to copy down the limit. So the limit stays right until the end, like I said. And then we're going to do, so remember by parts, I'm just going to write the formula here, uv minus integral v du, just as a reminder. Now I'm going to sub in my values. So I have x e to the 3 minus x over negative 1. Now I get this, I'm just going to change it. The dividing by minus 1 is just going to come to the front and make it a minus 1 in front of the x. So that's what I'm going to do here. I'm just erase that, and I'm just going to put a negative right there. And remember that I'm evaluating from 9 to t. You don't want to forget the evaluation sign. And then minus integral v du. Okay, so I'll get 3 minus x all over negative 1, and then times my dx. Now again, this negative 1 will cancel with this negative 1 in the middle, but I'm going to do that the next step, and then we just got to not forget our 9 and t. Okay, so moving along. So then again, I keep my limit as t approaches infinity, and then I get negative x e to the 3 minus x. I'm not going to evaluate it yet. I'd rather do that at the end. And here I'm going to get the integral of 9 to t e to the 3 minus x dx. Again, because of that minus 1 in the bottom right there, and this minus right there, they cancel each other to become a plus. Okay, and then continuing onwards. Okay, so I'm just going to continue right up here. And so I'm going to continue evaluating this integral. So the limit stays the same. This part will stay the same as well. And we will go from 9 to t. And then we're doing plus, and I'm anti-differentiating that part. So again, we've already done this before. This is divided by minus 1. Here, I'm just going to change that. So that minus 1 right in the bottom, and this plus, they will become a minus. So I'm just going to replace that right now instead of going to the next step and doing that. Okay, so I'm going to put an x there. Okay, then I'm also just going to wipe that out and just put a minus right there. And again, I'm evaluating from 9 to t. Okay. All right, so now I'm going to evaluate my integral, plugging in the bounds, and then take the limit. So plugging in t, I get negative t e to the 3 minus t, and then plus, remember that it's a minus, but there's a double minus there. And this is going to be 9e to the 3 minus 9. And then minus, I'm going to put this part in brackets. I get e to the 3 minus t, and then minus e to the 3 minus 9. Okay, so I'm going to simplify this before taking the limit. We might as well do that. So I get negative t e to the 3 minus t. Okay, now notice here, I get a 9e to the minus 6. There's the exponent. And then here I'm going to get a minus e to the negative 6 as well. But this minus is also going to cancel it out. So I'm just going to write it out. 9e to the minus 6. And then minus, okay, let's write the 3 minus t. And then I'll get plus e to the minus 6. Okay. Carrying onwards, limit t approaches infinity. And then minus t e to the 3 minus t. Okay, let me just bring this term right in the middle because that one has a t in it. The other two I'm going to combine. So this one here, and then the e to the negative 6, that becomes plus 10 e to the minus 6. I'm just collecting like terms there. Okay, and now I'm just going to evaluate the limit. So basically what I'm doing is I'm subbing in infinity everywhere I see t. So what I'm going to get is basically minus infinity e to the, now I'm doing 3 minus t, so 3 minus infinity, which is minus infinity, and then minus e to the, again, minus infinity, because it's 3 minus a big number, and then plus 10 e to the minus 6. All right, so I'm going to just carry on up here. Okay, so for Math 1M, which is the course I'm doing this for, you haven't done L'Hopital's rule, and you have most likely haven't done it in the previous course either. So what I would say for this part here is, okay, this is going to become minus infinity times, and then e to the negative infinity. It's like doing e to the minus 100, for example, which is going to be a 0. Now, this is problematic because you need L'Hopital's rule to evaluate this, and you don't do this in this course, but I'm going to explain it at the next step. Again, the e to the minus infinity, that's like e to the minus 100. This will be a 0. This will be a number very close to 0, and then plus 10 e to the negative 6. Okay, so for this underlined part, the minus infinity times 0, I'm just going to go to the bottom of the screen here. Minus infinity times e to the negative infinity. Basically, this is going to be a 0. We're looking for which one of these two goes faster, and it's going to be the e part. There is a result in your textbook that gives this as well, but without going into too much detail because you haven't done L'Hopital's rule, this part will be 0. Okay, so anytime you get basically a t and an e to the negative something, that limit as t approaches infinity will always be 0. Okay, so you get 0 minus 0 plus 10 e to the negative 6, and this is just going to be 10 e to the negative 6. All right, and then for terminology, so since the integral equals a real number, then we say that the integral converges or is convergent. And that's the end of the question. Okay, now let's take a look at an example that has both bounds as plus and minus infinity. So in this case, we do need to split that up into two different integrals and then evaluate them together. So what you want to do with these integrals is you want to split them up somewhere in between. Usually it's a good idea to choose 0 as long as the function is continuous at 0. So this function is continuous everywhere. The only two problems are the bounds, the minus infinity and the plus infinity. So you want to split it up into two and then do each of them separately. Now remember in the other one, we split these up into limits. So I'm going to do that right now. We're going to have limit as t approaches so not 0, but I should say minus infinity, and then we're going to have a t and then a 0, and then everything else stays the same. And then the second one, we're also going to set up a limit. I use the same letter. I'm not sure if there's a preference, but I personally use t again just so that it's not confusing. 0 to t, x cubed e to the negative x to the 4 dx. Now what I would suggest to do is if we look at the integral, basically this is going to be a case where we would use substitution. If you want to use by parts, it's way too complicated for by parts, but I notice that it's substitution because if I let u equal to the inner part of the integral, which is minus x to the 4th, its derivative is going to be negative 4x cubed, which the x cubed is right there. I can see it in the integral. So it's a good idea to use substitution. What I'm going to do though is I'm going to first evaluate this integral without any bounds. With substitution, if you don't change the bounds, if you don't do it without the bounds at the beginning, it might be confusing when you bring in a u, and then you've got the x's, and then you've got the limits with a t, so it's a little bit confusing. So I personally would evaluate it without the limits first. So let's go from here and say, okay, let u equal to negative x to the 4. That means that the derivative of that is negative 4x cubed dx. And that also means that dx is going to be equal to du divided by negative 4x cubed. So all I'm doing is just solving for my dx. Now I'm going to sub it into the integral. So I'm going to get integral of x cubed e to the u. So the negative x to the 4 becomes a u. And then the dx, we've already solved for that. And that's going to be du divided by negative 4x cubed. Okay, carrying on from there, well, we notice that the x cubes are going to cancel out. So we are left with basically e to the u over negative 4 times du, which I prefer writing as negative 1 over 4 integral eu du. Just bring the constant out. And then this is an easy integral to evaluate. It's just going to be negative 1 over 4. The antiderivative of e to the u is just e to the u. And then just at the bottom, I'm going to put in what u was, which is negative x to the 4. Okay, so there is my answer to the integral without bounds. So what I'm going to do now is go to the limit and basically evaluate this, put the 0 and the t into there, and then take the limit from there. And I'll show you how to do that. Okay, so I erased the part about substitution, and we're just going to go straight into the integral now that we have evaluated it. So basically from here, I know that the answer to my integral without the bounds was negative 1/4 e to the negative x to the 4. We just did that on the other screen. And then we're going to evaluate this from t to 0. And then same thing for the other integral, just a different limit. We're taking it as t approaches infinity. Same answer because we did that without bounds. And then this is going to be from 0 to t. Okay, remember to sub in your values before doing the limit. So I'm going to do that right now. So basically I'm subbing in the 0 first, negative 1/4 e to the 0. And then minus, and then this evaluated basically at t. So this becomes a plus because there's a double minus there. E to the negative t to the 4. Okay, that's that one limit. And then the second limit is going to be t approaches infinity. Something similar except the reverse. So this is going to be negative t to the 4. And then again, double minus is a plus, e to the 0. And we will carry in from there. Okay, so then if I look at the first limit, if I put in minus infinity into there, so I'm going to get negative a quarter. Now it's e to the 0. E to the 0 is 1, so I don't need to rewrite it. And then plus a quarter e to the negative, and it's going to be infinity, or it's going to be, sorry, negative infinity to the 4. So I'm going to write it out like this for anybody who wants to see all the steps. And then I'm going to do plus, and then I have negative a quarter e to the negative, and now it's infinity to the 4, and then plus a quarter e to the 0 again, which is a 1. Okay, so I get negative a quarter plus, and this is going to be a quarter e to the, now be careful here, negative infinity to the 4. It's like doing, let's say, minus 1,000 to the 4. It's going to be a big positive number, and then you've got that extra minus on the outside. That's going to be a minus infinity. Be careful, only the minus inside the brackets right there. That's the only thing that will get taken to the exponent of 4. Okay, and then we get plus, I guess I could change this to a minus at this point. So it's going to be minus a quarter. So I'm going to remove the brackets, and then e to the minus infinity. Same idea here, and then plus a quarter. Okay, so if we evaluate this, I get minus a quarter at the front, plus, now again, remember e to the minus infinity, this is 0, so times a quarter, that's 0. And then minus, again, 1/4 times e to the negative infinity, e to the negative infinity is 0. And then I get plus a quarter, and this is all equal to 0. So 0 is the value of my integral. And just like the other case, since the integral is equal to a real number, in this case it's equal to 0, then we can say that the integral is convergent. And that's the end of the question. Okay, so let's do another example that's a little bit different than the ones we've done so far. So in this one, we're asking for what values of the constant p does the integral from 1 to infinity 3x over x to the p dx converge? Okay, so this is a little bit different because here we cannot get a real number, or we can't get a definite answer out of this integral because of the value of p, which is not known to us. The variable is still x, but p is a constant, but we need to define which values of p will actually give me a real number for this. So what I'm going to do is I'm actually going to attempt to evaluate it for as far as I can, just like I've done before, and then split it into cases. Okay, it's improper again because of that infinity bound. So I'm going to say t approaches infinity, and I'm going to go from 1 to t, 3 over x, x to the p dx. And in order for me to evaluate this, I do have to make it look a little bit nicer. I don't want to start thinking about doing, let's say, by parts, because that's way too complicated, or even substitution. It's a little bit easier than that. I'm going to do 3 times x. Okay, there's a 1 on the x, so I'm doing x to the 1 over x to the p. This is just exponent subtraction, just exponent laws. I do 1 minus p dx. This makes it a little bit easier because then I have x to a power, and I can just integrate the way I usually do. Okay, so we're going to keep the limit on the outside. If you put it the way I've done it, basically you don't need to use by parts, you don't need to use substitution. This is just more or less a straightforward integration. The 3 is a constant, so I keep it. The x, I'm going to just add 1 to the exponent like I've always done. Just pretend it was like x squared. You would add 1 and get x cubed. And then divide by that exponent, 1 minus p plus 1. Oops, I'll just write that a little bit nicer. And then we'll go on. Okay, this is being evaluated from 1 to t. Just going to simplify it a little bit to see if we can do something about that. So I get 3x to that. Now it's 1 minus p plus 1. So I'm just collecting like terms to get 2 minus p all over 2 minus p. And again, we're evaluating from 1 to t. Okay, so then we're going to sum in the values for our bounds, and then at the end, split it into cases so that we can evaluate the limit. So what I'm getting here is 3 times t to the 2 minus p. So just subbing in t for x, and then 2 minus p. This part is a little bit confusing because you're not subbing in the bounds for p, you're subbing them in for x. That's the variable here. Then I'm going to do minus 3 times, okay, I'm going to do 1 to the 2 minus p. So I'm going to write it out first. But 1 to the anything is just 1. So I'm just might as well just leave it as a 1 and then divide it by 2 minus p. Okay, so there it is. So now you get this integral. And to be honest, I'm just going to scratch out that one. It's a little bit redundant there. Okay, so now let's split it into cases and see where it would be convergent. Okay, so the toughest part about this question, I think, is actually the step right now, which is, okay, what do I do with it now? Because if you were to sub in infinity for t, depending on what the value of p is, you'll get a different answer. So let's try to split them up into cases. What I would do is case 1 is the most obvious, and it's if p is equal to 2. So basically, if p is equal to 2, then we get 0 in the denominator. The limit will not exist. So we could say limit doesn't exist. And therefore, we can say that the integral is divergent. Okay, so this one is a little bit more straightforward. Again, just try it. Put a 2 in the denominator, you'll get 0 there. Anything over 0 does not exist. Okay, so that's case number 1. Now we're going to go on to case number 2. Case number 2, now try to work around the value of p. We said that p equals 2, the limit doesn't exist. What if p is, let's say, less than 2? Okay? Okay, then we get. Now, what you could do is take concrete values if you want, just to just to make it look a little bit easier. Then we get example. What we would get is, let's say, limit as t approaches infinity of, okay, if p is less than 2, let's say p is 1, for example, you'd get 3 times t all over 2 minus 1 is 1, and then minus 3 all over 1. And this limit would be equal to infinity, because you would do 3 times, you would put infinity for t, so you put infinity right there. 3 times infinity is infinity, minus 3 is still infinity. Okay, so in this case, we would say that it is divergent as well. Now, I chose 1. You could choose anything less than 2. Like, let's say p equals 0, p equals -1. It doesn't matter. All of those cases will always give you a limit that's always equal to infinity. So that's case 2. And then what remains is case 3, which is if p is bigger than 2. Okay, so example, what we would get is limit as t approaches infinity of, not the integral, pardon me. We would get 3 times, okay, a number that's bigger than 2, let's say 3. So you would get t to the 2 minus 3, so you'd get t the -1 all over -1, and then minus 3 all over -1. Okay, so in evaluating that limit, we would just basically, if you put infinity into the t to the -1, you would get, so I'll just rewrite it here in case you want to see the steps. So you would get -3. I'm just combining that -1 with the 3 to get me -3. And then the t to the -1 would go to the bottom. So if you write it out like that, it's a little bit more straightforward. I'm just going to cut this part up. Okay, and now if you put infinity into the denominator, you're going to get -3 over a huge number, which is a small number, close to 0. And here you're going to get 0 plus 3 equals 3. So in this case, you could say that it is convergent. So let's just take a look at our screen for a second. If p is equal to 2, the integral will be divergent. If p is less than 2, the integral will be divergent. If p is greater than 2, then the integral is convergent. So I'll write the result on the next screen. Okay, so I've summarized the results here. So to answer the question then, the integral would converge if p is strictly bigger than 2. And that's how we do that question. I hope this video has helped clarify the concept of improper integrals and how to do questions on them. So thank you for watching, and good luck.